Good afternoon, dear PTC 2022 members. I am Ayush Gupta, a master's student at Skolkovo Institute of Science and Technology. Today, I am glad to present to you SwarmHive, Heterogeneous Swarm of Drones for Robust Autonomous Landing on Moving Robot. Heterogeneous teams of mobile robots and UAVs are offering a substantial benefit in autonomous exploration, inspection, and delivery. By 2028, autonomous last mile delivery market is expected to exceed 51 billion US dollars from 8.78 billion US dollars in 2020. The growth of autonomous last mile delivery market is led by the development of aerial delivery drones. However, last mile delivery to remote areas remains still challenging for companies across industries due to high cost of repairs and the low efficiency of the drones missions. Meanwhile, multi-agent systems are still suffering from low adaptability to changes in external conditions. One of the most challenging tasks is swarm docking on a ground station. Several researchers have been recently exploring the means to improve the robustness and the accuracy of UAVs landing on a moving platform. Some of them use control systems for large swarms for landing on platforms and predictive control for collision avoidance in accordance with the outdoor conditions. But they don't take into account the constraint of the landing platform dimensions and the internal collisions between the swarm agents. We propose SwarmHive technology, a heterogeneous swarm of drones capable of landing on a moving ground robot with a small landing area. The novelty of this project is the multi-agent system with vision-based tracking and collision avoidance for safe landing of UAV swarm on a moving platform. The overall system includes two types of heterogeneous robots: a swarm of drones and a mobile robot. Each swarm agent consists of Raspberry Pi, a Pi camera on a rotating mechanism, allowing the camera to be used both horizontally and vertically depending on the task. A Raspberry Pi controller for computer vision processing, and Crazy Fleet 2.1 flight controller. For drone localization, we use Vicon motion capture system. The Bitcraze Crazy Fleet firmware was used to control the drones via ROS. The ground station PC receives the updated positions of all the drones from the mocap system and landing target position from the leader drone through ROS topics, from which it calculates the swarm target trajectory using continuous feedback-based planning. The proposed SwarmHive system is capable of landing on a moving platform while avoiding inter-agent collision using visual tracking and visual tracking of the landing zone and the artificial potential field method. For the detection of the target landing site on the moving platform, we use most recent visual fluidical system APL 3 with OpenCV and ROS as a bridge to pass the coordinates to the fluidical markers. With the help of this system, we estimate the position of the possible tags on the image using graph-based image segmentation algorithm and obtain a visual estimation of the possible tags more accurately than GPS systems. In addition, we tested the algorithm with tags of different sizes and opted the size of 16.6 by 16.6 centimeter based on the robust tag detection at wide range of distances. A leader drone can detect the tag at maximum distance of approximately 3.5 to 4 meters and a minimum distance of 30 centimeters. By tracking several feature points between two consecutive frames of video, we can robustly estimate their motion, then compensate for it. The tracker algorithm works better with textured regions and corners, assuming that the pixel intensities of an object are the same with every frame of the video. And we can track similar motion in neighboring pixels. To find the difference in the intensity of the displacement in all direction between the original and the move window, the Lucas-Canada optical flow method was applied. While the swarm is out in the threshold zone, the swarm operates in formation flight mode, flying in triangular formation to land on moving platform. The formation is held by a virtual structure that can change its orientation based on the yaw angle of the target platform, thus landing safely using artificial potential field algorithm. Artificial potential field is implemented as the sum of the two virtual potential fields, attraction and repulsion. The attraction potential field, which pulls the drone towards the target waypoint, is defined in the second equation. The potential is proportional to the square of the distance between the drone's current position and the target position, where zeta is the scaling factor. The repulsion potential pushes the drone away from obstacles. In the third equation, the drone isn't affected by the obstacle's repulsion unless the drone is within the distance d naught from it. The shorter the distance rho from between the drone and the obstacle, the higher the repulsion, and vice versa. Thus, the drone can avoid collision with the obstacles. By calculating the artificial force acting on a drone from combined potential, we can correct the drone trajectory to reach the target while avoiding the collision. A two-part experiment was carried out to evaluate the proposed approach of SwarmHive landing. First, landing on static mobile robot, and second, landing on a moving mobile robot with several velocities. At the start of each experiment, the drone, a leader drone, was followed by other agents' attempts to find the target. While in moving condition, the swarm tries to land on it. The swarm of drones used in the experiment includes one leader drone, which weighs 0.262 kgs, including a 450 mAh 3S battery, and a follower drone of 0.032 kgs, each including a 240 mAh 1S battery. The onboard processor for the leader drone is Perminov 2.1 firmware with quad deck extension and Raspberry Pi 4 with Pi camera recording RGB frames of images of 640 by 480 pixels at a rate of 30 FPS. Whereas the follower drones include Crazy 2.1 controller. Each experiment was repeated 10 times, resulting in over of 40 trials. In this experiment, the mobile robot is set to a stationary position, and the swarm of drones is launched. The leader drone has to find the April type, and the follower drone moves according to the received trajectory coordinates. After 10 landing experiments, the overall RMSE of the swarm formation landing was 4.48 centimeters. The experimental results revealed that the drones landed within the cross proximity of the target. Moreover, the RMSE does not depend whether the drone performs as a leader or as a follower. In this experiment, the mobile robot moves in a straight line trajectory. The trajectory is calculated at different velocities of the mobile robot. That is 0.5 meter per second, 1 meter per second, and 1.5 meter per second. As the mobile robot moves, the swarm of drones follows the robot's trajectory without changing their landing formation by yawing until they land on the target location. In this condition, we observe that the drones identify the target tag, they start to move towards it, and go into the landing state as the certain threshold is achieved. The overall RMSE for the swarm formation at 0.5 meter per second, 1 meter per second, and 1.5 meter per second are 6.3 centimeters, 8.76 centimeters, and 8.98 centimeters respectively. 10 experiments were conducted at different velocities of mobile robot for a total of 30 experiments. The experimental results revealed that the drones land in the close proximity of the target. However, the RMSE increases along the speed of the moving platform. The experimental results reveal that the proposed computer vision based strategy for the landing of the swarm on a moving platform is capable of safe landing up to 1.5 meter per second platform velocity, up to 4 meter initial distance of the platform, and the RMSE threshold for 15 centimeters. The RMSE does not increase significantly when the rover velocity increases from 1.1 centimeters to 1.5 centimeters, as we limit the velocity of the drones to prevent the crash. Also, the velocity limit of the drones will explain the choice of the rover speed for the experiments. To support swarm landing on mobile platform with higher velocity, it is required to investigate more complex target estimation algorithms in combination with artificial potential field and model-based state prediction approaches. We propose a novel technology, SwarmHive, which allows a swarm of heterogeneous drones to land on a moving platform with limited surface area. The computer vision based system was developed to detect the visual tag and calculate its distance from the plane. The artificial potential field approach ensured both the following visual tag and the prevention of the internal swarm collisions. The experimental results revealed a low landing RMSE error of 4.48 centimeters and 8.98 centimeters in the cases of static and moving platform respectively. The proposed SwarmHive project can potentially significantly improve in the scalability of the mission task, thus expanding the area of applications, flexibility of the functions that can be performed in real life by accumulating data from different sensors and systems. In the future, experiments on different flight conditions and disturbances, the studies will be continued. Thank you for your attention.